Okay. Today I want to talk about identifying outliers because I think especially in your projects, but also just in general, some of the most interesting cases and the most interesting stories come from these outliers, right? If you're able to kind of identify the outlier and what's going on and things like that. And a lot of times outliers are inconvenient in that you're trying to find some overall general trend and the outliers there and it doesn't fit the overall trend. So you just kind of want to throw it out. But, and maybe for the overall analysis, you might choose to throw away an outlier or something. But a lot of times the most interesting cases, the most interesting stories or whatever are housed in these outliers. Like, for example, if you look at, I don't know, travel data and whatnot, there's going to be a huge outlier in the year 2020. Why? Because there was the COVID pandemic, right? And if you're looking at overall trends and stuff, it might be like, oh, well, that's inconvenient. Let's ignore this. But we lived through that, and it would feel strange to just kind of throw away this part of history just because it is seemingly inconvenient or something. So, for overall trends, maybe we should remove it, but certainly I think it's to look into it and say, oh, what is the reason for why this data is so different from everything else? Why is the reason for this data point being so different? And there's often a big story or something behind it. But then there's always kind of this question, well, what counts as an outlier? What counts as an outlier? And so I'm going to provide some guidelines. There's no hard rule that says, okay, well, this is the outlier and this isn't the outlier. But I'm going to show you a few kind of general trends or general ideas that we can use. And then, one of the most basic things is use your intuition, okay? If your intuition says, well, that looks strange, then yeah, probably it is, okay? So trust yourselves, I guess, okay? So an outlier, all right, is basically something that is quite a bit different from beyond. It's basically the outlier is more different than what we consider to be normal differences, okay? So to kind of get an idea of what is our normal amount of differences and whatnot, is we use the concept of variation. Variation is basically how similar are our values to each other. And so if we're looking at numeric values, we can measure variation. And if the values are very similar, the variance, and the standard deviation will be small. And if the values are quite a bit different, our variance and standard deviation is going to be quite a bit big. I just had this weird feeling of deja vu right now. I didn't do this lecture already, did I? Okay. Do we go over the formula for standard deviation already? Or variance? No. Okay. All right. Does that ever happen where it's sometimes you just wait a second, I feel like I've been in this moment in the universe before. Okay. All right. Sorry. That was weird. All right. Okay. So I haven't taught this. I don't know why my brain was just you were here before. Okay. It's glitch in the matrix. Okay. What was I saying? Okay. So yeah, imagine visiting an elementary school. You go to a second grade classroom and you're like, how old are all the kids in this classroom? And in a second grade classroom, probably everyone's going to be 7 or 8 years old. Okay. And if you have somebody who's 10 in that second grade classroom, that would feel like an outlier, right? And you'd be like, oh, what's this? Why is there a 10-year-old in the second grade? And they might be like, oh, well, that student, their family just immigrated from another country and the student didn't speak English at the beginning of the year, so we wanted to kind of ease them in or something. And you're like, oh, okay, well, I guess that makes sense or something. But otherwise, you're kind of expecting everybody in the second grade classroom to be like 7 or 8, and anything really outside of that just feels a little bit strange, okay? If you go to a college classroom, right, most of the students will be, 18, 22, kind of like this 4 or 5 year time span after high school. But of course, you're going to have people older than that. And so it's not that strange to have like a 27-year-old in a college classroom, And so, if you think about like a 2-year difference in the second grade classroom, like someone who's 2 years older than everyone else, that feels a little bit out of place in the second grade classroom. But in college, if someone's 2 years older than everyone else in the classroom, that doesn't feel that strange, right? So you have more variation, more spread there, okay? And then if you visit, urgent care, okay, and you think about the ages of people at the doctor's office in urgent care, you're going to have babies, and you'll have seniors, and you'll have adults and teens, and everybody in between, right? So you have this huge spread in ages. It would not be strange. Nobody would be like, why is there a 1-year-old here? Okay, that person doesn't belong. And nobody would be like, why is there a 95-year-old person here? That person doesn't belong. Whereas, it would feel a little bit strange if there's a 1-year-old in your college classroom or a 95-year-old in the college classroom. You're like, whoa, why is that person here, right? And so who's an outlier very much depends on the context and how much kind of spread and variation there exists in the rest of the data. And so, we would say the second grade classroom has little variation. The waiting room at the urgent care office has lots of variation. And rather than just saying little and lots, we can quantify it with a number. And so we've seen things like we've been calculating these summary values, like we've been doing like group by and summarize and give me the standard deviation and give me the variance and things like that. But yeah, I don't think I ever showed you the formula for those things. And so we'll cover the formula and the concept of these things. So the variance, we can think of it as the average of the squared distances from the mean, okay? And the symbol for the variance is S. Standard deviation is the square root of the variance. So when you go into dplyr, the tidyverse, and you say group by age and give me the standard deviation height, okay, we get a sense of the average squared distance from the mean or the square root of the variance. And so the formula for the variance is this. We take each point x, we subtract off the mean x bar. That's going to give us how far the point is from the mean. We're going to square that distance, and then we take the average by adding them up and dividing by n minus 1, okay? And then the standard deviation is the exact same formula, but you just throw it inside a square root, okay? So here is a simple example. If I have the numbers 1, 2, 3, and 10, the mean of these numbers is 4, right? 1 plus 2 plus 3 plus 10 is 16. 16 divided by 4 is 4. And and we want to calculate the distance from the mean. Did I ever explain? So when we do the mean, like we all know how to do this. We just add them up and we divide by how many we have. And we probably learned this like in 4th grade or something, and then you saw it again in 7th grade or whatever, right? Like, so the concept of the mean is very familiar to us. But what it is doing is it is balancing distances from itself. It is balancing deviations. I don't think I explained this concept. And let me see if I can kind of, where's paint? All right, am I able to draw this? So I don't know if my fingertip will work here. Oh, look at that. Okay, so here's our number line. 0, 1, 2, 3, 4. Okay, here's 5, 6, 7, 8, 9. All right, 10. Okay, and let's say I have points at how do I? All right, I want a fat brush. Oh, here. This is what I want. Okay, so I'm going to put a point at. That's too big. Okay, a point at 1, 2, 3, and 10. Okay. If I said, hey, where's the median? The median is the spot where you have 2 points on the left and 2 points on the right. Okay, you want to find the middle point, and the median balances the number of points that are below the median and the number of points above the median. So you have 2 below and 2 above. Okay, the mean. Okay, so this one would be the median. The mean, however, and I'll put this in blue. Okay, would go like right here at 4. I am not a graphic designer, as you can see. But okay, so that's the mean. And what it's doing is it's balancing the deviations from the mean. Okay, so the deviations from the mean is basically like, how far is this point from the mean? Well, it's 1 away. How far is this point away from the mean? It's 2 away. How far is this point away from the mean? It's 3 away. Okay, so you have the deviations are, you have deviation equals 3, basically distance from the mean. And here you have deviation 2. Equals 2. And here you have deviation equals 1, right? And basically that's the distance from the mean. I guess these are all technically -3, -2, and -1. And then over here for 10, how far is it from the mean? Oops. Its distance is 6 away, okay? This distance from 10 to the mean, this deviation is 6. Okay, so as far as the deviations above the mean is 6, and the deviations below the mean is 6. And so you have these, you've balanced the deviations or the distances from the mean. That's what the mean does, okay? So, and you do it by adding them up and dividing by how many you have, and that will give you the mean. So the mean balances the deviations, whereas the median balances just the number of points. And so because the mean balances the deviations, if you have a number that's like way huge, so we see it a little bit with this number 10, our mean gets drawn up to 4. But if I had like one value that's at 100, so if I have 1, 2, 3, and 100, okay, because that 100 is so far up, my mean has to be like way higher, right? 1 plus 2 plus 3 plus 100 is 106. 106 divided by 4 would give me 26.5, okay? And 26.5 would balance out the deviations from the mean. But it gets dramatically kind of pulled in the direction of that outlier. So anyway, the mean is 4, and so we're going to find the distance from each number in the mean. So these are the deviations. Okay, so 1 is 3 away, 2 is 2 away, 3 is 1 away from the mean 4, and 10 is 6 away from the mean 4. So we're basically calculating, okay, what are all of these deviations? We have 3, 2, 1, and 6. And then we're going to average the squared deviations. Okay, so we're going to do 3 squared, 2 squared, 1 squared, and 6 squared. We get 9, 4, 1, and 36. And then what's the average of these? 9 plus 4 plus 1 plus 36. If I add those up and divide by how many I have, that would be 50 divided by 4. Now, I don't want to get into it, but it turns out that if you're trying to estimate the standard deviation of the population, that number is going to underestimate, and so we actually divide by 3 rather than 4. We add these up and divide by 3, and then so my variance, my quote unquote, so I put average in quotes, we add them up and divide by n minus 1, we get a variance of 16.67. Okay, so this is what we have. Now you might wonder, like, why are we squaring the distances rather than just like, why don't I just do this? Why don't I just take the average of the, like absolute values of the deviations? Yeah, that does exist in statistics. It's called the mean absolute deviation. There are some mathematical properties of the variance that we prefer, like you can take derivatives of it without any kind of problems. Absolute values, there's like a corner, and that creates a discontinuity in the variant in the derivatives, and then there's other issues. But anyway, we end up squaring the distances. Okay, so you square the distance, and we take the average of these things, but the average is in quotes. We add them up and divide by n minus 1. And so my variance is going to be 16.67. The standard deviation is going to be the square root of that, and I get 4.08. And these are the exact numbers that you get if you go into R and you say, hey, give me the variance, 1, 2, 3, of 1, 2, 3, and 10, and you get 16.67. Give me the standard deviation, and you get the square root of the variance. Okay, so that's where those numbers are coming from. It is basically calculating the mean, calculating how far each of the points you have are from the mean, and then squaring those, and then kind of taking the average. Okay. And so, another example, before I forget, I always forget, is your first view quiz answer today is the letter E. E as in elephant. E. Billy Joel. Okay. Is there first view quiz answer? Okay, so here's just another simple example where we could see the variance measures the amount of spread. And so imagine we have two families. We have the Baker family, we have the Cook family. I guess these are the occupation last names. And both of them have 5 kids. Both families have 5 children. And in both families, the mean age of the children is 9. Okay, and you go, oh, okay. 2 families, 5 kids, average age is 9. But what are the ages? In the Baker family, from youngest to oldest, the ages are 1, 3, 9, 13, and 19. And in the Cook family, from youngest to oldest, the children are 7, 8, 9, 10, and 11. Right? And so if you imagine what does life look like in the Baker family and what does life look like in the Cook family, life looks quite a bit different, right? Probably in the Baker family, this kid is going off to college. This kid is still in diapers, okay? Whereas in the Cook family, they're all like very similar in age and things like that. And so just looking at these numbers, we know there's more spread in the Baker family and there's less spread in the Cook family, okay? So mentioning only the number of children and mentioning the average age doesn't really capture the full picture. So we can go through and we can calculate the variance. And we could just type these into R, but I'm going to go ahead and just kind of do it by hand. And so, again, the mean age is 9. You add them up, divide by 5, you get 9. And we're going to say, okay, how far away is each of these numbers from the mean? So 1 is 8 away from 9, and you square that, you get 64. 3 is 6 away from 9. You square that, you get 36. And 19, you go through it. 19 is 10 away from 9, and you square that, and you get 100. So your numbers are 64, 36, 0, 16, and 100. You add those up, you get 216. You divide by n minus 1. We only have 5 numbers, so we're going to divide by 4, and we get 54. And the standard deviation is going to be 7.348. Okay, and again, if I type this into R and I say 1, 3, 9, 13, 19, and I say, what's the standard deviation? I get the same number, 7.348. All right, and this is the formula for getting that. Same thing for the Cook family. We do that. Our standard deviation is much smaller, 1.58. Okay, so our standard deviation confirms exactly what we knew without having to calculate the standard deviation. But we could say, okay, the Baker family, ages in the Baker family are more spread out. And we can say the standard deviation of ages in the Baker family is 7.35. Standard deviation of ages in the Cook family is only 1.58. Now, this is an obvious case where we can see the difference very easily. But, in other cases, you might not be able to tell which group has a larger standard deviation, especially if you have hundreds of numbers, right? So if you're in your data, you might have a whole bunch of numbers, and you might say, okay, this variable measures, I don't know, the cost of, I can't think of something. I'm drawing a blank right now. But, you might have some kind of variable where you have a bunch of different numbers, and you might have another variable with a bunch of different numbers. And you might wonder, which of these numbers exhibit more variation? Well, the standard deviation is a way for us to kind of measure that. All right. You guys just saw the penguins in your midterm, and here I wanted to, I don't know, was that fun at all with the penguins? Did anyone look up what these penguins look like? How do we pronounce these? Adelie? Whoa! I thought it was going to pronounce the name, but no, we hear what it is. Okay, well, look how cute they are. Okay, the Adelie penguin? I don't know how to pronounce. Oh, how do you pronounce? Look at that. Adelie. Okay, look at that. All right. Now, Adelie. No, I don't know. Penguin is pronounced. Okay. Oh, wait. Adelie. Okay. All right. Well, here's the Adelie penguin. And then we also had
I think Gen 2.
The Gen 2 and the chinstrap? Okay, those were the, yeah, all right. This is chinstrap penguin. Oh, so cute. He does have a little chinstrap. Okay, and then the Gen 2 penguin. Well, that looks, man, I don't know enough about penguins. Okay, well, anyway, there you go. Chinstrap penguins. All right, so anyway, we can ask to plot this. And so here we're going to look at bill length and bill depth. Okay. Oh, here's a diagram of what exactly we were measuring. Okay, so on the penguin, I don't know how the researchers did this. Did they have to chase the penguin and then capture them and then take a measuring and be like, well, we're going to measure your thing? I wonder. Okay, but anyway, this is the bill length and this is the bill depth. And, in your analysis, you get different things. And as we would expect, the length of the bill is longer and the depth is shorter because we're getting, length is longer and the depth is not as big. And so, when you plot this, here is the histogram of bill length, and we can see, okay, on average, it's like 45-ish with, and we have more spread, okay? And then as far as bill depth, the average looks to be 18, I don't know. This is all, did I filter? No, this is all of them, okay. And this is what we have here. We have different bill depths, and we can say, all right, what is the mean bill depth? The mean bill depth, I guess, is 17, and the standard deviation is around 2, okay? And then as far as bill length goes, the mean is around 43, 44, and the standard deviation is 5.46. And that aligns with what we see visually, and what we would also imagine is well, what we see visually is that there's more spread, right? The values in the histogram are literally more spread out, okay? And over here, the values are less spread out for bill depth. So this matches that we have more variation in bill length. And so as far as the values go, 43.9 and the standard deviation, 5.46, okay? And now we can introduce this concept of a z-score, okay? A z-score is how far an observation is from the mean expressed in standard deviations, okay? So to get a z-score, we just take the observation, we say how far is it from the mean, we subtract off the mean, but we're gonna express it in standard deviation. So if each standard deviation is like 5.5 and the mean is 44, if we have an observation at say 49.5, that has a z-score of 1. It is 1 standard deviation above the mean, okay? And if we're at 49 plus 11, that would take me to 60. 60 would be, about 2 standard deviations of the mean. Its z-score would be 2, okay? So here's a question. Which is more unusual? An Adelie, what was it? Adelie? An Adelie penguin with a bill depth of 20 millimeters, or a Gen 2 penguin with a bill length of 55 millimeters. Okay, so where's my... so which one's more unusual? Okay, so what we have to do is we're going to look at the Adelie penguins, and its mean bill depth is 18.3. So we're asking, okay, what about a 20 millimeter bill depth? So it's going to be above average. The standard deviation is 1.22. So what is that? What's its z-score? Versus a Gen 2 penguin, where the average bill length is 47.5 and the standard deviation is 3.08, is a Gen 2 penguin with a bill length of 55 millimeters more unusual. So we'll just kind of plug this in. So if I do the Adelie penguin with a bill depth of 20 millimeters, we can say, okay, well, if the average is 18.346 and this one is at 20, okay, that's what, 1.7-ish above the mean. Each standard deviation is 1.2, so it's around 1.359, 1.36 standard deviations above the mean. Its z-score is 1.36. The Gen 2 penguin, compared to the mean, is above the mean by about 7.5, and each standard deviation is around 3. So it's 2.4 standard deviations above the mean. So if you look at the z-score for the Gen 2 penguin, it is farther away from 0 than the Adelie penguin with a bill depth of 20 millimeters. Okay, so that would be the more unusual observation there. So you compare not just the direct value, but you want to divide by the standard deviation to see how many standard deviations away from the mean it is, okay? And that's how you can kind of compare, which of these things is more unusual, right? Again, it's kind of like, what would you say is more unusual to see? A 10-year-old in a second grade classroom or a 24-year-old in a college classroom, okay? And I think we would say the 10-year-old in the second grade classroom, even though 10-year-old is maybe only 2 years above average in the second grade classroom, we'd say that feels unusual because the standard deviation of ages in the second grade classroom is very small. So 10 years is quite a significant departure from what we see in the second grade classroom, okay? Whereas in college, perhaps the average age in that college classroom is 20, okay? And so we have a 25-year-old, that's 5 years above average there. But you look at the standard deviation, and you have a much bigger standard deviation, and so 5 years above average doesn't feel all that weird. Seeing a 25-year-old student in a college classroom is not unusual, whereas seeing a 10-year-old in a second grade classroom does feel unusual. And that would be revealed in our by z-scores. Okay. All right, so here is kind of a plot of this. So just more of these things, you pivot the things longer, and then you do ggplots and stuff. Okay, so here I have the bill depth. And so for looking at the Adelie penguin, we can see the 20 millimeter Adelie bill length would be right around here. And then if we look at 50, so we can see, I don't know, it's kind of hard to judge, but we can see, all right, it's above average, but also not that extreme. Whereas 55 millimeters above, for the Gen 2 bill length is way out here. I have a way to draw or annotate this. Okay, is way out here, which is considerably, I think would be unusually high compared to all of the other Gen 2 penguins, right? There are penguins with bill lengths, Gen 2 penguins with bill lengths of, 59, 60, and things like that, but pretty rare compared to everyone else. So we'd say, yeah, the 55 millimeter bill length is unusual. The 20 millimeter bill depth is high, but not that unusual when we're talking about the Adelie versus the Gen 2 penguins. Okay, and we can, this is another thing we can do is we could say, okay, well, let's look at all of the penguins we have, and we can say, okay, well, how many of them, if I filter down to Adelie penguins, how many of them are over 20 millimeters? And we can say, well, there were 18 out of 133 plus 18 is like 150. So out of 150 penguins, 151 penguins, 18 of them had bill depths over 20, okay? And over here for the Gen 2 penguins, how many of them have bill lengths over 55, okay? And there were only 3 out of 123. So, just by kind of looking at the counts or even the proportions here, we can say, yeah, there's, very few Gen 2 penguins with bill lengths over 55. And there are, not a lot, but, over 10% of Adelie penguins have bill depths over 20. So, again, this just confirms basically what we saw with our z-scores and with our histograms. And so, yeah, if in your, in your own projects and whatnot, okay, you will come across some kind of interesting observation or something, you might want to say, hey, you know what, let's look at this value and if it makes sense to calculate a z-score, you can use a z-score. If it makes sense to calculate, what proportion of other observations are above or below this value, these are things you can use to kind of corroborate whatever point you're trying to make, okay? So when you're dealing with z-scores, these are kind of rules of thumbs that we have, but it's important to say this only applies if you have data that is unimodal and symmetric, which basically means looks kind of like a normal distribution. Unimodal means there's one peak, and symmetric means, kind of symmetric looking. And so if it's unimodal and symmetric, about 2/3 of your observations, 68%, a little over 2/3, will have z-scores between 1 and -1. And then the vast majority, around 95%, will have z-scores between 2 and -2. And so only a few, like 5% of observations will have z-scores beyond 2 or -2. And then almost all, 99.7%, so almost all will have z-scores of between 3 and -3. And so if you end up with a z-score greater than 2 or more negative than -2, you can say that's pretty unusual. And if you have a z-score above 3 or more negative than -3, that's considered highly unusual, okay? These rules don't apply, though, if the data is not symmetric. So if you have something that's very skewed data, basically like the histogram looks kind of like this. You have kind of this long tail over here, okay? This is something that's skewed. And so this could be something like income, right? You have 0 and maybe 200K. All right, so like the vast majority of people make between 0 and 200K. But then you have millionaires and people whose incomes are millions of dollars a year. And, well, if this is the scale, here's 400 and here's 600 and technically like 800,000 is out here and 1 million is like way over here. And this tail is very, very, very long and goes, very far to the right? $1 million, $5 million a year. Some people with sports contracts get, 30 million a year and things like that. So you have this very, very, very skewed distribution. And if that's the case, then this Z-score business doesn't really make sense. Now, if you do have highly skewed data, you can apply a transformation, like you can take the log of every single number, or you can take the square root of every single number, and that might transform your values into something that makes more sense. Okay, I've given you one answer so far. Okay, let me give you your second answer. Your second V-quiz answer is the letter C. C as in cat. C as in cat. Okay, we have a tool, box plots. Box plots are displays that we can use, visualizations we can use that also kind of identify outliers in the process of making the box plot. So you have these percentiles, the 25th percentile and the 75th percentile. And so, a lot of times you see these numbers reported for like college admissions and stuff. They'll say like the middle 50% had GPAs between like 4.1 and 4.4 or something like that, right? Like you look at admission statistics and stuff. And so anyway, you have the 25th percentile and the 75th percentile, and then kind of the difference between those numbers is calculated and called the interquartile range. And then a box plot basically makes a rectangle for that interquartile range. And then from the box plot, you have these whiskers that go out to the smallest and largest values that are not considered outliers. So I'm going to kind of just skip ahead here. And so in this data set, I've got these numbers: 3, 5, 5, 7, 7, 8, 9, 10, 10, 10, 10, 14, 20, 21. Our median is 9.5. And if I find the 25th percentile, it would be 7. If I look for the 75th percentile, it would be the number 10. So my IQR is going to be 3. When you make a box plot, you get, there's these invisible boundaries called the lower fence and the upper fence. The lower fence is going to be Q1 minus 1.5 IQRs, and the upper fence is going to be Q3 plus 1.5 IQRs. These are, again, just this is just a loose guideline for determining what is an outlier. And if you use the box plot method, it says figure out your interquartile range, which is the difference between the 25th percentile and the 75th percentile. And it says, okay, and then from that 75th percentile, the Q3, go up 1.5 IQRs, 1.5 of that distance. And then from the first quartile, the 25th percentile, go down 1.5 IQRs, go down 1.5 of that distance. And these are going to form these invisible boundaries called the fences, the lower fence and the upper fence. And we're going to say anything above the upper fence here is going to be considered an outlier. Anything below the lower fence over here, it would be considered an outlier. And so if we apply that to our data set, okay, my IQR is the difference between 10 and 7 because my first quartile, Q1 is 7, my third quartile is 10, so I have an IQR of 3. So if I do 10 plus 1.5 times the IQR, okay, 10 plus 1.5 IQRs would be 14.5 because my IQR is 3, 1.5 is 4.5, 10 plus 4.5, 14.5. So anything above 14.5 is considered an outlier. So 20 and 21 would be considered outliers. If I do the same thing on the lower side, I do 7 minus 4.5, that gives me 2.5. And if I had any values below 2.5, those would be considered outliers. I don't have any values below 2.5. The smallest value I have is a 3. So I don't have any outliers on the lower side. Okay. So when I draw my box plot, it looks kind of like this. The whisker goes down to the 3. That's the smallest data point I have. The whisker goes up to 14. That's the largest point that's not an outlier. And then points 20 and 21 get represented with dots to indicate that they are outliers. This goes from 7 to 10 to indicate Q1 and Q3. Sorry, it looks a little bit funny, but this is our box plot. And you can do this by doing ggplot, geom box plot. And this is what we have. So this line right here is Q1. This line over here is Q3, 7 to 10. The width of the rectangle is my IQR. And basically, if I go up 1.5 IQRs, that takes me to 14.5. And that would be, there's like an invisible line right here for my upper fence. Anything above that is considered an outlier. So in this case, we would say 20 and 21 are outliers. If I do this for the penguins, okay, so here I would just take my penguins. I'm going to put bill length on the x-axis, and for we're going to separate them by species, okay. And so, as far as the Adelie penguins, okay, this is, let me see if I can pull this up here. I want to compare I want you to see the comparison between the box plot and the histograms. It's a little bit hard to see. Okay, so here we're only looking at bill length. Okay, so we have Adelie chinstrap Gen 2. And then for box plots, for whatever reason, they put them in reverse order, okay, with Adelie on the bottom, then chinstrap, and then Gen 2. And you can kind of see that, yeah, this reflects the same distribution, right? The center of the Adelie penguins' bill length is lower compared to chinstrap and Gen 2. And that's what we see. The chinstrap has the highest kind of median. Gen 2 is a little bit lower than the chinstrap median. And we also get a sense of any kind of outliers. And so as far as our data goes, only this one observation, the Gen 2 penguin with a bill length of like 60, basically this one observation out here, is the outlier. And looking at the histogram here, it does appear that this one observation is kind of, a little bit different from everyone else. So that is the one outlier. But apparently, no outliers for Adelie and no outliers for chinstrap. There is kind of a lot of spread, and that's reflected with the fact that you have long whiskers. But this part right here, the box represents kind of the middle 50%, okay? And so you have like the middle 50%, 25th to 75th percentile, not a lot of spread here. But then, yeah, if you look at the whiskers, there's more spread, and then we have an outlier for this one Gen 2 penguin with a very long bill length, okay? And so, as you're doing your projects and whatnot, it could be interesting to create a box plot or do some kind of z-score analysis to see, hey, do we have anything where we have z-scores over 3 or even over 2? to see if you have things that are highly unusual. And you can also do a box plot to see if you have observations that are considered outliers. And then if you're able to, try investigating those things, especially if you have like public records and stuff. So if you're looking at like sports data and you find some outliers, usually you can look up like that player name or that team or something, and you can be like, oh yeah, this was like this one superstar player that really kind of like stood out compared to everyone else. Okay, and so those are always kind of interesting. Okay, so that is just some information about how we might go about identifying outliers. And let me give you your last view quiz answer. Last view quiz answer today is the letter B. B as in bear. Okay. Just a couple of housekeeping things. So next week is week 9, and then we have week 10 and week 11. And so I'm going to post on Brew and Learn, or actually, well, I guess on the same spreadsheet where you signed up for proposal meetings, I'm going to put on another sheet where you're going to sign up for final presentations, okay? And so final presentations will take place during week 10 and week 11, and I know everybody, your instinctual thing is probably like, I want as much time as I can, and so to incentivize people signing up for presenting during week 10, just so we can kind of spread things out, I will offer some extra credit for the week 10 presentations, just to kind of incentivize it. And I'm trying to find the right balance where it's like, I don't want to offer too much extra credit where everyone's like, oh, I need to get like, the point of offering the extra credit is to try to space out the presentation. So I'm not dealing with like 6 presentations in one day, but I'll set up a schedule, and that will happen like during week 9. Okay, so just a heads up for there, and yeah, enjoy your weekend. We have Monday off, so we'll see you guys on Wednesday, and yeah, good luck as you guys continue working on your final projects. I hope they're coming along. And again, if you have any questions, like if you have an idea, like you have a question with your data set, and you're like, we want to be able to do this. We're not quite sure how to go about it, and like writing the code or how to pull this apart in the data, like I'm happy to give you advice and help. I do feel like this is something I am pretty good at. So don't hesitate to come, especially if you have good questions. I'm always happy to help you explore these good questions. Okay. All right. Have a great weekend, and we will see you on Wednesday.